Welcome to lesson 3.5. The topic here is exponential and logarithmic models. So we're going to go through several examples in this lesson. I want to teach you the 5 basic kinds of models that can model real-world problems. Number 1, exponential growth, exponential decay, the Gaussian model, which is very important in probability and statistics, logistic growth model, and logarithmic models. So that's where we're going to focus our time today. This year we haven't focused too much on the graphs themselves, mostly on being able to solve exponential and logarithmic equations. We are going to concentrate on the graphs eventually, but at the beginning I felt it was a better review to focus on how to solve exponential and logarithmic equations. So what we want to do now is we want to look at the different kind of model problems that you're going to be encountering. Example 1. Online advertising. Estimates of the amounts in billions of dollars of U.S. online advertising spending from 2007 through 2011 are shown in the table below. A scatter plot of the data is shown in the following figure to the right. An exponential growth model that approximates these data is given by the following equation. S equals 10.33 e to the 0.1022t. Time is from 7 to 11, 2007 to 2011. S is the amount of spending in billions of dollars. So now we have a context for the problem. The model generates a graph which generates ordered pairs which approximate the data or model the data. So let's compare the values given by the model with the estimates shown in the table. First, let's look at the algebraic solution. The following table compares the two sets of data, advertising spending figures. So, the advertising spending is 21.1, 23.6, 25.7, 28.5, and $32 billion. That comes from the data. The model, which is the equation which tries to represent the real world, has values that are pretty close, but they're somewhat off, and that's to be expected. The reality is our models won't be able to perfectly represent what's going on in the real world, but they should represent it closely, okay? So to find the amount of U.S. online advertising spending when it will reach $40 billion, we substitute. We let S, which represents the advertising spending, equal 40. And now we have an exponential equation. Divide both sides by 10.33 billion. Take the natural logarithm of both sides. Finally, divide both sides by 0.1022. And we end up with time, which is 13.2, which means that according to the model, we'll end up with $40 billion of spending in about 2013. The graphical solution will take the model and then graph the model and then use the zoom or trace feature to figure out when y is equal to 40. Using that feature, we get that y is equal to approximately 40 billion around 13.3. So this is another way of coming about to the same solution. Okay, let's look at another kind of model problem. Modeling population growth. In a research experiment, a population of fruit flies is increasing according to the law of exponential growth. Now after 2 days there are 100 flies, and after 4 days there are 300. How many flies will there be after 5? Now because we're told that the population is being modeled, or is according to the law of exponential growth, we use the following model. We use y equals a e to the kt, or something of that sort. Which, let's go back to the beginning page so I can see the model with you again. Right here. Y equals a constant, e to the bx, where b is greater than 0. So that's the model that we're going to use. So we take the things that we know. We know that y equals 100 when t equals 2. And we know that y equals 300 when t equals 4. Substituting this information into the model, we get two equations. 100 equals a times e to the 2b, and 300 equals a times e to the 4b. To solve for b, solve for a in the first equation. So divide both sides by e to the 2b. So a equals 100 over e to the 2b. Then substitute that result into the second equation. So 300 equals a times e to the 4b becomes 300 equals 100 over e to the 2b times e to the 4b. And then we use the subtraction property of powers. E to the 4b minus 2b is e to the 2b. Divide both sides by 100, and then take the natural logarithm of both sides. Natural log 3 is equal to 2b. So the constant b is actually 1/2 natural log 3. Using b equals 1/2 log 3 and the equation that we found for a, we can determine that a is equal to 100 over e to the 2 times that value of b, which is 100 over e natural log 3. But e natural log 3 is the number 3, and so a is approximately 33.33 fruit flies. So with a being approximately 33.33 and b equaling 1/2 natural log 3, which we approximate to 4 decimal places as 0.5493, we now have a complete model. Now we can finally answer the question, how many will there approximately be after 5 days? All we need to do now is replace t with 5, and we get approximately 520 flies. Let's check out the following carbon dating problem. Now, carbon dating only works on living organic material. That's important. In living organic material, the ratio of the number of radioactive carbon isotopes, which is called carbon-14, to the number of non-radioactive carbon isotopes, which is called carbon-12, is about 1 to 10 to the 12th. When organic material dies, its carbon-12 content remains fixed, whereas its radioactive carbon-14 begins to decay with a half-life of about 5,700 years. To estimate the age of dead organic material, scientists use the following formula, which denotes the ratio of carbon-14 to carbon-12 present at any time, t in years. So one thing that we have to do is get a handle on what half-life is. So let's say I have a half-life of 5,700 years, and let's say I begin with 100 grams of the radioactive substance. Well, what that means is, the half-life, is that after 5,700 years, since I began with 100 grams of the substance, after that time passes, I now have half as much. So I now have 50 grams of that substance. If another 5,700 years passes, then I have half of that half, which is 25 grams. If another 5,700 years passes, how many grams will I have? Well, I'll have half of 25, which is 12.5 grams. And that's the idea behind half-life. Half-life is a time period, and when that time period passes, you only have half as much of the substance as you had before. Now, R is considered to be the ratio. Time is considered to be in years. And so the model that scientists use, the carbon dating model, is R equals 1 over 10 to the 12, e to the negative t divided by 8223. Estimate the age of a newly discovered fossil in which the ratio of carbon-14 to carbon-12 is R equals 1 divided by 10 to the 13th. So we have two different approaches here. We have an algebraic solution, which we'll go through first, and we have the graphical. So let's look at the algebraic. In the carbon dating model, substitute the given value of r to obtain the following. 1 over 10 to the 12th e to the negative t over 8223 equals r. We replace the r with 1 over 10 to the 13th. And we multiply both sides by 10 to the 12th. This gives us e to the negative t divided by 8,223 is equal to 1/10. Now we natural log both sides. The natural logarithm of e to this power will simply become negative t over 8,223. The natural logarithm of 1/10 becomes negative 2.3026. Multiplying both sides by negative 8,223, we get the time period, 18,934 years. So if this model is correct, then to the nearest 1,000 years, the age of the fossil is about 19,000 years, according to that model. Graphical solution. Using a graphing utility to graph the formula for the ratio of carbon-14 to carbon-12 at any time, we take the model as they gave it to us. We call this y1. But we also put a y2 into our calculators, which is simply the constant, 1 divided by 10 to the 13th. And we use the intersect feature in our calculator by going to second calc. When we find out when the two curves intersect, we get that x is approximately 18,934. So again, to the nearest 1,000 years, the age of the fossil is about 19,000 years old. Let's look at a Gaussian model. As mentioned at the beginning of this section, Gaussian models are of this form. Y equals a e to the negative quantity x minus b squared divided by c. Now, this type of model is commonly used in probability and statistics to represent populations that are normally distributed. You get what's called a bell-shaped curve from the normal model. Let's look at example 4, SAT scores. In 2008, the Scholastic Aptitude Test, the SAT, math scores for college-bound seniors roughly followed the normal distribution given by the following model and the following condition. Y equals 0.0034e raised to the negative quantity x minus 515 squared divided by 26,912. The condition is that x must be between 200 and 800, where x is the SAT score for mathematics. Now, what is it we want to find? Sketch the graph of this function from the graph, estimate the average ACT score. So again, we're looking for the average. That's what we're trying to find. So the graph of the function is shown as follows, 200 to 800. The average will always be located at the dead center of the bell-shaped curve. 50% of the population will be above that value, above the average, which makes sense, and 50% of the population will be below that average. And so, in this case, the average value for SAT score was 515. All right, these are actually some of my favorites. I like logistic growth models. I like solving them. Some populations initially have a rapid growth followed by a declining rate of growth, as indicated by the graph in the following figure. And so here we see the curve representing population. It's increasing, and actually this point right here is when the rate of increase is the largest. But after that point, the population, as it still increases, it's slowing down and it's increasing. And so it comes to some constant value. So logistic models, the first thing you need to know is that they have a horizontal asymptote. The logistic curve is given by the following model. Y equals a over 1 plus b e to the negative rx, where y is the population size and x is the time. An example is a bacteria culture that is initially allowed to grow under ideal conditions, and then under less favorable conditions that inhibit growth. A logistic growth curve can also be called sigmoidal curve, a sigmoidal curve. Let's look at example 5, the spread of a virus. On a college campus of 5,000 students, one student returns from vacation with a contagious and long-lasting flu virus. The spread of the virus is modeled by the following formula. Where time is under this condition, it must be greater than or equal to 0, but that makes sense. Where y is the total number of students infected after t days, the college will cancel classes when 40% or more of the students are infected. So this is a two-part question. How many students are infected after 5 days? And secondly, after how many days will the college cancel classes? So let's solve these two parts both algebraically and graphically. Now after 5 days, all we need to do is plug 5 into the formula and then evaluate. So after plugging 5 into the formula, we get approximately 54. And so y represents what again? Y is the total number of students infected after t days. And so that means that 54 students will be infected, approximately 54, after 5 days. Now, classes are canceled when the number infected is 40% of the student population. 40% of the student population is 2,000. And so here we set the logistic model equal to 2,000, we substitute, and replace y with 2,000. Then we multiply both sides by the denominator, 1 plus 4999 e to the negative 0.8t, and at the same time, we divide both sides by 2,000. So think of it this way, put the 2,000 over the number 1, cross the denominator up, and cross the numerator here down. This gives us 1 plus 4999 equals e to the negative 0.8t equals 2.5. Subtract 1 from both sides. Take the natural logarithm. Divide by negative 0.8. Then we find our approximation. So if the flu continues to grow unabated, then after about 10 days, at least 40% of the students will be infected and the college will cancel classes. Graphically, using our calculator, we would plug this model into y1. And then we would simply use the vars key, vars, yvars function y1, and plug in 5. This would give us about 54 students. In order to solve the problem for how many days it would take until the college cancels classes, we would let y1 be our model and y2 would be the constant 2,000. Again, we would go to second calc and use the intersect feature on our calculator to find out where the two curves meet. And that would be at about 10.1 or 10 days. Let's look at the logarithmic model. Magnitudes of earthquakes. On the Richter scale, the magnitude, capital R, of an earthquake of intensity I is given by the following. R equals common log I over I naught, where I naught is equal to 1, is the minimum intensity used for comparison. Find the intensity of each earthquake. Intensity is a measure of the wave energy of an earthquake. So, part A, Nevada in 2008, R measured 6.0. In eastern Sichuan, I think I pronounced that wrong, but Sichuan, China in 2008, R measured 7.9. So what was the intensity for the two? Because we're using the initial intensity as 1, we substitute. 6.0 equals logarithm of I over 1. Because this is common log, the base is 10, so we make 10 the base of both sides. And that gives us that I is equal to 10 to the 6.0, which is 1 million. So the intensity is measured as 1 million. For R equals 7.9, we have 7.9 equals common log I. making 10 the base of both sides, we get I equals 10 to the 7.9, which is 79,400,000. Note that an increase of 1.9 units on the Richter scale, from 6 to 7.9, represents an increase in intensity by a factor of 1 over the other, which is 79.4. In other words, the intensity of an earthquake in East Sichuan was about 79 times as great as that of the earthquake in Nevada. And those are the examples for this particular lesson. God bless you, wherever you are today.